you. Okay, so in this talk, we will talk about polynomial commitments. Well, not really about where to find them, but I hope you get the reference. For the start of the talk, I will introduce polynomial commitments schemes. This R is for relaxing. You have already been like listening a lot about commitment schemes, so this should be easy. Then where to find them, also relaxing, almost a joke. The importance of KCG. So KCG is like the polynomial commitment we will try to talk about today. So I will kind of ignore everything else and try to drive you to KCG. And this is for confusing because we will start talking about the importance of KCG without me introducing KCG to you. So this is to get you hyped. And then we will talk about KCG. This is the important part. Then we'll go back to the importance of KCG, which is how it helps us to build snarks. This may be confusing, but it's also important. And at the end, we'll have an example of how to build a snark using the help of KCG. And I have never done an example of building a snark in a talk before, so not really know whether this will be confusing, relaxing, important, or let's see. So what are polynomial commitments? Polynomial commitments were introduced by Zapico and Goldberg in 2010. They are commitment schemes where the space of messages is the space of polynomials. So as all the other commitment schemes, it has a setup phase that takes as input security parameter. In this case, also bound on the degree of the polynomials that we can commit to, and output some public parameter. There is a commitment phase where the input is the public parameters and a polynomial. The output is a commitment to this polynomial. And then we have the open of the commitment. In this case, the open of the commitment, opening a polynomial will mean open a polynomial at a certain point. So this opening phase will evaluate the polynomial in a point that is an input to this algorithm, alpha, and output the result of the computation with a proof that this opening is well performed. And then the verifier will take the commitment, this point, the claim evaluation, and the proof, and decide whether it trusts or not the output of the open. If you see this as an interaction between two parties, a prover and a verifier, the setup is an algorithm that is run by an external party. Let's say the prover can commit and then open the polynomial, and then the verifier is the one that wants to get convinced that indeed f evaluated in alpha is s. The first day there was a bit of confusion on why I cannot open. I remember when Jonathan was giving this example of the matrix, that you commit to the matrix and then you open. Well, the thing is that the verifying algorithm takes the commitment as an input. So me as a prover, I can commit to the polynomial and later open it. And the verifying algorithm has to connect the previous commitment to the opening. So I don't know the polynomial as a verifier, but I know that this opening corresponds to the commitment that the prover sent to me before, or publish, sorry. So as any commitment scheme, we have the normal, the common security properties. Completeness says basically that if the setup and the commit phase are run honestly, and also the opening is run honestly, meaning that f evaluated in alpha is indeed s, well, the verifier has to accept with probability 1, right? So this is perfect completeness. Then our notion of binding is evaluation binding. That means that any adversary, polynomial time, that is able to choose the commitment to come up with an element that claims it's a commitment to polynomial alpha, and then two openings of f of alpha to two different points must fail. Will never be able to convince the verifier except with negligible probability. So same concept of binding. I cannot open the same thing to two different things. I cannot say f of alpha is S1 and it's also S2, right? By definition of a polynomial. And then hiding also, as the notions we saw in the first day, assumes the existence of a simulator that can simulate the interaction between the verifying algorithm and the commit and open algorithm, and no adversary can distinguish. Informally, let's say what it means is that by interacting with a prover that has committed to the polynomial, I cannot learn anything else about the polynomial. In this case, I cannot learn other openings of this polynomial more than the one that the prover is telling me. So, where can we find polynomial commitments? Where have you found polynomial commitments in your research life?
Cryptocurrency.
Of course, cryptocurrencies. Where else?
Snarks.
It's not cryptocurrencies, you know. They are everywhere on ePrint. And but there is something curious here. So polynomial commitments were introduced in 2010. So I look for the citations on KCG. And between 2010 and 2018, KCG has around 125 citations. After 2018, until now, so without counting these ones, we have 576. Well, cryptocurrencies may have something to do here, but I will say that the one to blame here, oh, wait, I forgot I had something. So why is that KCG got so much importance? As Carla mentioned before, we have, before, let's say 2018, we have two kinds of setups, a trusted setup or a transparent setup. In the trusted setup, as Growth 16, we have a very good efficiency, but we have to trust someone. Whereas in the transparent setup, we have a not so good efficiency. We will see what not so good efficient it means later, but it's good. We don't have to trust any other parties. We are cryptographers, so we love it. And in 2018, what happened is that not Sonic. There was a paper in crypto by Grotz and others, Marcus among them, that introduced the universal and updatable structured reference tree. So it's something between the transparent and the trusted setup. Again, this was mentioned by Carla before, where instead of just trusting one party, we have a process that is run by different parties asynchronously, and they all collaborate to this setup. If one of these parties is honest, we are okay. In particular, we can be part of the process if we don't want to trust anyone. And now we have a trusted setup that is not trusted, not transparent, but something in the middle. And the efficiency of the protocols that we can build with this updatable SRS is also in the middle of them. It's not as efficient as Growth 16. We haven't got there yet. And it's way more efficient than protocols with a trusted transparent setup. So shorter proofs, faster verifiers, and for now, just that. So this is the updatable part of the SRS, but also the universal part of the SRS. Again, something that was mentioned by Carla, is that this SRS can be reused. So, and it's not only that you can use the same SRS for different circuits, you can use it for different proving systems, for different snarks. You can use the same SRS for something like Marlin and also for a vector commitment. So it's really something that is not so expensive procedure that pays off because we can keep using it. So the paper that introduced universal and updatable SRSs came out with a construction where the SRS was quadratic, the size of the circuit. So not very practical, but few months after, Mahler et al. In Sonic, also Markov among them, introduced the first snark that has a universal and updatable SRS that is linear on the size of the circuit. So let's say the first universal and updatable practical snark. And Sonic look a bit like this. So this is the main protocol in Sonic. And so what I highlighted is that they use as a building block a polynomial commitment scheme. So if you see here, the first one is the prover, computes some polynomials, commits to them, the verifier sends some random element, prover commits to another polynomial that uses that random element, more random elements, and then the prover opens a bunch of polynomials and the verifier verifies, and only accept if this checks all paths, right? So the flavor of Sonic, or what Sonic said without necessarily like building yet a framework, was that we can build snarks from KCG. We can use KCG as a building block for snarks, and those snarks will have also an updatable and universal SRS as KCG does. For that, one important thing is that snarks are proof of knowledge. So what they have to prove is that KCG is extractable. So we have that KCG is a polynomial commitment, so it satisfies completeness, evaluation binding, hiding, and also they prove that under certain assumption actually in the algebraic group model that we will see later, KCG is extractable. What does it mean? It means that there exists an algorithm, the extractor, same notion as we saw on Monday, that from the commitment can extract the polynomial. And then all proofs that verifies with respect to that commitment say that these are opening proofs for that polynomial. So from the commitment, I can extract a polynomial. And then if you say that this commitment opens to S in alpha, means the polynomial output by the extractor opens in alpha to S, except with negligible probability. So
Is there any guarantee that the polynomial you extract is unique?
Is there any guarantee? Yes. Under certain, so you have a bounded degree, and then depending on the basis you choose, you will extract one. I mean, the polynomial is the same. Sorry, I was thinking about the vector. Well, then that was a hype about KCG, but let's see what is KCG, how it works. Probably some of you know, but please stop me if you are lost somewhere. So it's a polynomial commitment scheme. So we have a setup that takes as input some security parameter, a bound for the polynomials I can commit to, and outputs a structure reference tree. How? First, it has to generate a group description. We work over bilinear groups. And actually, I thought Carla will have introduced some notation that I will introduce now. So if P1 is a generator of G1, I would say that A times P1. I will denote it, sorry, like this. Right? And the same for the second group. Notation introduced by Raffles and others that I thought was going to be introduced in the lecture before, but I will use this additive notation. So we need to work over a group. Then this setup phase sample tau is a trapdoor, must remain secret, must be uniform and remain secret. And then it outputs what is called a structure reference string, because it has a structure. I will have the powers of tau in both groups. Well, actually, if you see the first two powers, so 0 and 1 are in both groups, and then I just need the rest in group 1. But for now, it's the same, if you can think of it. And if you see, this is updatable, because if I come with a new element mu, I can multiply this element mu times, this element mu to the square times, this element mu to the 3 times, and then my new trapdoor will be tau times mu. But I don't know tau, and if I don't tell mu to anyone, no one will know it. So, and it's universal because it doesn't say anything about the relation I'm proving, just powers of tau, of a secret element. So that's enough for KCG. In the commit phase, the prover uses these elements in the group and do linear combinations with the coefficient of F to get F evaluated in tau in group 1. So the prover does this by not learning tau at any moment, right? Just because in this group, something is worth mentioning, the discrete log problem is difficult. tau is kind of like hidden on the exponent, and then I can manipulate it only with field elements. But that's enough to do my evaluation of f. To open this polynomial at a point alpha, well, the prover first calculates what is the value of f when evaluated in alpha, and then it will calculate, and we will see in a minute why this works, the quotient coefficient of f of x minus s divided by x minus alpha. This division is possible because when x is alpha, f of x is s, basically. We will see it again in a second. And then that's the proof by, right? So the prover outputs s and a proof that s is the correct opening of f. And the verifier will take the commitment that the prover sent at the beginning, s, which is a field element, claim output of the computation, and check whether this is divisible by tau minus alpha. So this tau minus alpha is x minus alpha evaluated in tau, right? Because we want to work with the pairing, so everything goes to the group. This was already given by us in the group. This is something that the verifier can compute. It will take it only one exponentation. And this is also something the verifier can compute. So the only thing I don't care about here as a verifier is Q. I just need that Q exists. So that x minus alpha actually divides f minus s. The shape of Q is not of my interest.
The commitment is the group element and S is not, am I right?
No, well, yes, you have to do the
Oh.
exponentiation. Yes, sorry. It's the pairing. The pairing of my bilinear group. So, but you saw pairings in the previous talk. Oh, sorry, that was my bad for not coming. So a bilinear group.
Can have, if you want, we can have full whiteboard. That's an amazing feature here.
I know, but I think I can use it here.
Oh, this one, yeah, it's a bit hidden maybe.
So this generator that I put at the beginning will output the description of a bilinear group that has some order P. We call them two groups, G1 and G2, and another group that we call the target group. Okay, but can you see that? No, right?
Mostly we can, but
Okay. Let's do it here. So the description of my group will give me the order of the group, two source groups, a target group, and two generators. Not missing nothing, right? Okay, and sorry. The bilinear map E. E goes from G1 to G2, and G2, sorry, to the target group. And it has this property. So what a pairing allows me to do is to check the multiplication, is to check the result of the multiplication of two elements that are in different groups.
What do you mean by check?
I mean, you can compute the multiplication. So I can take an element in G1 and an element in G2 and multiply them. But the multiplication of these elements will end up in GT, in the target. Right? So what is even more, I can check the multiplication in the sense that, for instance, here I want to multiply two polynomials. Two polynomials that have secret elements. they are in the exponent. So how do I multiply two things that are in the exponent? So if I have g to the a and g to the b, can I get g to the a times b?
No, really not.
Why?
Because we can't.
It is called the
CDH?
computational Diffie-Hellman, right? So I cannot do this. But what happens when I want to multiply then two things that are in a group? I put one in the first group, the other one in the second group, and then I get the last one in the third group. Right? So I won't be able to compute A times B in G1 or G2. This is an abusion of notation. Please don't do this in your paper. So I won't be able to get A times B in G1 or G2, but I get it in GT. What is more, for instance, if I want to prove that A times B equals C, I can do my pairing, which will be like so for two polynomials that I don't have access to because they are in the group, I can still check some relation, only quadratic relations. I cannot multiply a third polynomial here unless we do some tricks, but that's another time, right? So I'm very sorry I didn't introduce it. But it allows us to check relations, quadratic relations between elements that are in the exponent of the generator of some group where the discrete log is difficult, so we cannot really recall.
Hello. If it helps, I just want to state that basically this verification is just checking this polynomial division at tau. So instead of having this indeterminate x, we now have tau there, and we are able to check this in this traptor tau basically. It helps us into it.
Yeah. So basically, look, the commitment is F in the group, in one of the groups. S is okay because it's a field element. So I can manipulate the field element as I want, but then Q is given in the group. So in order to multiply it by X minus alpha, I need to also put this polynomial in the group.
So there's a small typo. It should be brackets of S, right?
Sorry?
It should be brackets of S in the last line. Use that.
Yeah, but this is my abusion of notation. Sorry. Yes, S should be also in exponent. Why is that, for instance, Q it's evaluating tau here and it's in the group? Because of succinctness. Instead of sending you a polynomial, I send you one group element. But with succinctness, you lose information in this case.
That reference thing, the notation with the two subscripts, what would it?
This means that I give you G to the tau. So for a generator in group 1, I will give you G to the, well, G1, I call them P1 and P2. But I have the feeling that everyone likes more the other notation. So let's say we have G1 to the tau I, for I equal 0 to D. And then we also have G2 to the tau I only for 0 and 1. So if I want to compute a polynomial from here, I just have to evaluate this to the field element and then multiply. So I can do the group operations only. Linear combinations of what is in the exponent. In any case, we'll see the completeness of this. Usually if you read a paper on snarks, completeness follows by inspection, but this time we will try to do the inspection. So what does it say? Completeness says that if everyone behaves honestly, the verifier must accept. So let's start with this. If the prover behaves honestly, then it is true that F evaluated in alpha is S, right? Then F evaluated in alpha minus S is 0. No magic here. Or what is the same? F of X minus S has a root in alpha, right? Alpha is a root of this polynomial. What does it mean? It means that x minus alpha divides f of x minus s. Yeah, this is an equally if. Then q exists. So because this polynomial here is divisible by this polynomial, then I have a quotient, right? No rest, no anything. And now what we will do is move this to the group, because this is as in polynomial land, right? But this is a polynomial commitment. We want something that is succinct, efficient. But then if the commitment is actually f evaluated in tau in the group, which must be true because the prover is honest, and q is also what it has to be because the prover is honest, then the pairing will verify. So f of tau minus s equals q times x minus alpha. This is a typo because this is tau. This is basically using basic algebra. Jonathan said on Monday, at least what I consider I do is algebra, basic algebra, the basics of it, the most basic of it. So if f in alpha is s, then this must be true for some q. Okay, now we get a bit, it gets a bit more difficult with evaluation binding. So recall what evaluation binding says. I cannot claim f of alpha is S1 and f of alpha is S2. I mean, I can claim it, I cannot prove it. So let's suppose that our adversary actually outputs a commitment, an evaluation point, and two proofs, P1 and P2, that open to two different elements, S1 and S2. So we want to arrive to an absurd, basically. If that is true, then if both those proofs convince the verifier, then it means that these two pairings are valid. Like it is, these equations with pairings are true, and also that S1 is different than S2, right? So ideas, what can we do? Yeah, we can subtract. Both pairings are almost the same. They have just this and these elements that are different, and pairings are bilinear maps. So if we subtract this pairing, this pairing with this pairing, the first term survives, and we actually have the subtraction in the second one. So what we have, the commitment is gone because it was the same in both pairings, and here we have S2 minus S1 that is different than 0. Here we have just the generator of the second group. Tau minus alpha, it was the same in both, and P2 minus P1. So this is the part where cryptographic magic happens. So how do we prove that something is secure in cryptography? We prove that either it's secure or someone is doing something that they should not be able to. And in this case, what we should not be able to do is to compute tau minus alpha in the target group in the divisor. So the inverse of tau minus alpha in the target. We can do that. Why? Because S2 minus S1 is not 0. We can divide the other side of the pairing by that. And then we can, we will have that this give us the inverse of tau minus alpha in the target group. And I know this is very complicated, non-intuitive, and it is actually not intuitive, and this is why it's an assumption. So it's not that we arrive to something like 1 equals 0, so this is an absurd, and we are all happy. In cryptography, we use assumption. In snarks, when we have this much succinctness, we use awful assumptions. And in this case, what this assumption says is, I don't care how many powers of tau you have. In this case, from 0 to d, so all positive powers of tau, you will never be able to compute something like this. You will never be able to compute something meaningful with tau, that in this case is tau minus c inverse, even in the target. There are assumptions that are more intuitive. For instance, that given all these powers of tau, you cannot compute, for instance, tau times to the d minus 1. That is a bit more intuitive, right? Like I can give you as many powers of tau as I want, you won't get any information of tau. This assumption is basically made to work. So sometimes what happens is that we are trying to prove something secure, and we arrive to something like what we have here is not an assumption, so we make it up. But I mean, you have to explain why, no, right? Like you're gonna just come up with an assumption, but kind of works like that. So you can reduce it to another assumption that is well known, that we trust, that has been used before. But in general, this is how we prove the in this case evaluation binding of KCG, but many of the security of our protocols.
I just want to say, if anyone knows an efficient algorithm to do this, yeah, please let us know.
Yeah, please let me know. I will throw my thesis to like the bin. It's gone forever. But well, this is the assumption that we use to prove that KCG is evaluation binding.
How old is this assumption?
Sorry,
How old is this assumption?
I will give a guess and then the others can correct me. As old as KCG. Like my guess, no, because this is bilinear. No, but so this is bilinear. No, is that the S and the D are? No, it's strong difficult. But just that I saw the Ds and the S. But the bilinear one, when came out?
As old as the Dolev-Jampolsky, well, I guess, yeah.
As old as what? Sorry.
Yeah, I think it's early 2000s maybe, but yeah, as old as kind of there's a signature scheme based on this.
Okay.
Yeah.
That's true. There is a paper I like a lot, which is actually like a not a paper, but well, a document I think by Bonnet and others that Groth and others that put like lots of these assumptions together, compare them, prove reductions, what they are used for. I think that paper was clarify a lot in my mind. I can then
Gaddafi, I think.
Sorry?
Gaddafi, I think.
Yes, that one. But it kind of like give your adversary all the powers of tau, and let's see. Then let's prove that I cannot do anything meaningful with it. Well, then about hiding. Do you think this polynomial commitment is hiding? Well, I was pretty sure it was not hiding, but then yesterday I was reading the KCG paper, which I haven't read in many, many years because now we have manipulated KCG so much that it's not the explanation of it that we use. They say it's a bit hiding. Like, then they have another construction that is absolutely hiding. So they say because the discrete log is difficult in this group, you don't have anything. You don't know anything about this polynomial. Which may be true, but once you start opening the polynomial, like you start getting information about it. And more, what is more, like let's say I have a set of possible polynomials that I know you will commit to. I can just try them and check which one like gets the same commitment as this one, right? Because it's a deterministic commitment. So I won't get much into this, but they give another construction for a hiding polynomial commitment, which basically says, okay, if every time I open it to you, you get a bit of information of my polynomial, I will add a random polynomial and commit to both of them. When I have to open, I will have to open both because at the end, otherwise I'm never giving you the evaluation of F. But as soon as you ask me for less openings than the degree of this polynomial, I'm okay. So every time I open the polynomial to you, I leak a bit of information. But let's say this polynomial has a degree tau, t, sorry. Well, I have t chances of giving you information about F without giving you information about F. But then also the verifier has to change its protocol So any questions about KCG? So let's go back. And then we also, sorry.
One remark about hiding is that, like, if the simulator is allowed to get the trapdoor, you can basically simulate the queue of tau, right? So I think it really depends on how you define hiding. Here, I think it's a bit stronger, but if you relax, then yes, you can.
This is unconditionally hiding. But well, again, you need to know in advance how many times you will open your polynomial. So it's also a bit like tricky, let's say.
And I guess in general, like if you open at enough points, then polynomial is revealed anyway. So basically you can only hope to hide up to like, I guess if the degree is d, we can open up to d points, right? And if you have d plus 1, then you can.
Yeah, you can recover it. But if I add t other, like t more degree, well, once I give you more than 2 points, I'm starting leaking information. So about extractability, I won't prove it. But recall, we need an extractor that outputs a polynomial, and then we have to prove that that polynomial will correspond to all the openings, except with negligible probability.
Which model would you prove it on?
In the algebraic group model. So I'm not going to prove the extractability, but this is what is proven in Sonic. They use the algebraic group model of Push-Basher. I forgot the K. Killed and lost. So I will tell you intuitively what is the algebraic group model. It's a model to prove security of protocols, where we make a big assumption, which is that the adversary, so any other algorithm that wants to break our protocol, is algebraic. What does it mean that it's algebraic? That if it receives group elements, it can only do group operations on the group elements. It can only do algebra on the group, linear algebra on the group. So in particular, if A receives, I didn't put here as an index because this can be in any group. If I receive D elements in a group and I'll put an element, that element is a linear combination of those group elements and some field elements. So in particular, if I just output a random thingy, well, there are no coefficients. It's just the constant term of this polynomial is what I have. I didn't use the group element. But if I want to do something meaningful, I can only do basically linear combinations of what is in the group. So in KCG, in our case, what are the group elements that the adversary receives?
What did you mean with outputting something random?
What is output? So if you output something that is not related to your input.
Yeah, so can you do that?
Yeah, I can just sample an element and put it in the group. That's it.
That's not possible in the algebra.
AGM. I think there is an extension to AGM that.
Yeah, the one for the oracles, but I'm going to ignore it. But wait. Let me think for a second what I have just said. Well, yeah, it's a generator that I'm manipulating.
Yeah.
That was what I meant, sorry.
Yeah, sorry, I also would say like if you want to have a random group element, you just have to sample it by.
Put it on the exponent.
Yeah,
But then, yeah, you are using one of the elements that you are given that is the generator.
Yeah, absolutely.
But it's like the public. How are we time-wise? Okay, perfect. So in KCG, what are the elements that we all receive in the group?
For the powers of tau, which are kind of like.
So any adversary that wants to break KCG has information in the group. What is this information?
He said the powers.
The powers of some secret element. So if whatever I output is a linear combination of the powers of an element, what is it? What is a linear combination of all the powers up to the of an element? A polynomial, right? So basically, the algebraic group model says that for KCG, whatever a cheating prover sends to me, I can extract from there a polynomial. And that polynomial is evaluated in tau and it's in the group, right? So in particular, if the adversary sends me a commitment, from that commitment, I can output a polynomial. Then what is left to prove is that, so we know that this extractor works and doesn't fail because of the algebraic group model. then what is left to prove is that that polynomial that I can extract is actually the one that satisfies my relation, right? So this is a hint for extractability. You can try to prove it yourself. I will be glad to look at your proofs, but I won't get in the entire proof. You can also check it in the Sonic paper.
I want to say that here's actually the kind of setting where you would apply this type of reduction that we did for find rep to the log. Because in the algebraic group model, after in the proof, you reduce everything to the discrete log. And the trick is to embed information theoretically, these variables. So this is how the proofs in the algebraic group models always work using this trick.
So you did like a reduction like that in the.
Yeah, so like that's the point, right? Of the algebraic group model is that at the end, you're reducing everything to a standard assumption, which is like some kind of QD log.
Yeah, so that also gives a bit of the intuition that in the algebraic group model, when we have this kind of structured reference string, we can extract and then we work with polynomials. And this is what will come after this.
But then if you plug this KZG into our scheme, you have more group elements, no? How do you know that what you extract is the right KZG?
Because, I mean, you will have more group elements, but those group elements will correspond to different polynomials. Or you mean in the SRS?
Yeah, the SRS.
So in most of the snarks, the SRS actually is the same as for KCG. If you have something else, then you will extract a polynomial that uses, for instance, let's say you have, I don't know, all the powers of tau, but you also have, what do you have? Another element, an element that is called mu. Well, then you extract a polynomial x that will be evaluated in tau, and then you also extract some field element times mu. Well, let's say it's a bivariate polynomial, right? You always need to know the structure of the SRS, but then if the SRS has more elements, well, you will extract also linear combinations on those elements.
Just maybe follow up with a comment. It shows that composition is tricky in the AGM. Even if you're running this as a subroutine,
Okay.
elements flying around,
Yeah, that was my.
It's not. Okay.
I think most people ignore it probably. Potentially, like she was saying, usually all you have are the KCG parameters, but if you had other things going on, you'd have to really be careful.
Okay. And isn't there a way to make it, I don't know, extractable in something? I don't.
No.
Composable, you want. I mean, I think the only way to do it generically is to use different groups, which nobody's going to do in practice. And the other way, otherwise you just can't compose, and you just have to check it explicitly for the prototype.
If you have simulated proofs, it might just get very messy.
So basically, this is something that happens and has happened for me at least in many papers. You extract. I put like two sums of polynomials. Basically, I say, okay, this polynomial is a sum of two polynomials. The one I care and the one that I will prove that is zero at the end. So when you plug it in the proving system and you start extracting like information about the polynomial, you end up most of the times with the case that the other one is zero. And the other way around, when the commitment is using this, sometimes you have to add a check actually to make the other one zero. I can give you references for proofs like that. So back to the hype. So now we know what is KCG. Back to the hype that Sonic brought, we can kind of use KCG to build snacks. So this was, Sonic came out, I think, January 2019. I started my PhD like 3 months before, and then September was something like this. All these papers are like, I don't know, crypto, like HeroCrypt, very like widely cited. And all of them use the fact that we can build arguments of knowledge from polynomials and then compile them with KCG. We'll see an example of this. But this is a trend, and now you can see it not only in snarks, like in threshold signatures or simpler relations as vector commitments or lookups. We build with polynomials. Sometimes the proofs are done over the polynomials, and then we let KCG do the cryptographic magic here. And this is true for any polynomial commitment. So we can you can find it for other polynomial commitments, for lattice-based polynomial commitments, multivariate polynomial commitments. So it's not something that works only for KCG. Actually, here Spartan and Dark are not compiled with KCG. Plonk and Marlin are, and that's probably why they are the most famous. Because in 2019, as Carla said, we were in the verifier world. We wanted the verifier to be like the most efficient, will kill each other for just one group element less in the proof. And now, like, Spartan is back, or I mean, it's raising a lot because of all the papers that are kind of like hypernova, so linear prover. We'll see this again later, but it's like the foundation for all those papers. Lasso, Jolt. Well, then at the end, I think it appeared in 2020, got published in 2021, Lunar. And in Lunar, I like very much the compiler because all these papers were saying, okay, we can compile, we work over polynomials, we can compile with KCG. But it's not trivial how to compile with KCG. Because of, for instance, do you want hiding? You don't want hiding. How many times are you going to open your polynomial? Which kind of equations on the polynomials will you check? Are you checking quadratic equations? Are you like opening them in random points? Are you opening them in fixed points? So Lunar did a bit of a work by explaining all these parts of the compiler. And one of the theorems, you don't have to read it. One of the theorems that like explains this compiler basically says, if I have a PHP is a polynomial holographic proof, polynomial interactive proof, a proof over polynomials, so they were working with polynomials. So if you do a proving system with polynomials that satisfy certain properties, and you have a commitment scheme that satisfies certain properties, then you have an argument of knowledge that satisfies certain properties. So if you see here, for example, you need the PHP to be B plus 1 T bounding honest verifier zero knowledge. And your commitment scheme has to be leaky zero knowledge, BC leaky zero knowledge. Well, then your snark is trapdoor commitment honest verifier zero knowledge. It's not trivial to prove these things. Like they did a very, very impressive work, in my opinion, to have like everything in account. And this framework is super useful. I use it a lot. Work with polynomials, then call Lunar, make sure my polynomial LP satisfy all the properties they require, call KCG, and then the magic is done.
So if you go back a minute, I think that theorem is zero knowledge.
Yeah,
Can you
that's,
summarize it intuitively. What
you
is
can
it?
talk to Dario on Friday. I love Lunar, but once you get to understand it, it's one of the most useful papers ever. But yeah.
But the theorem is basically that what? That you can numerically compile polynomial.
It's part of the compiler. That if you have a polynomial holographic proof with certain characteristics,
Is PHP stronger than a polynomial commitment?
PHP is a polynomial interactive.
with
So that's the
with
information.
the holographic part, but it's like, yeah, the proving system in the polynomials. But I don't remember the context of this, but it's a universal commit and prove interactive argument. So there you also have at least the sounds. Well, let's be less snark. So I keep insisting, I like a lot KCG because it gives us the opportunity to work over polynomials and just don't care about everything else. And I prepared an example. I hope it goes well because I came out with that yesterday. But we'll try to do a proving system, a snark, to solve the following problem. Let's say we have a prover and a verifier. They both have access to a polynomial, right? And then given some basis, they have degree at most d minus 1. And given a Lagrange basis of the polynomials of degree d, that is built with respect to a set, right? So the Lagrange basis says that Li will vanish at every point in H except of the one corresponding to the one. And this is the vanished polynomial of this set. So this is an input for both prover and verifier. We had two polynomials. We have a basis for the polynomials of that degree. And then the prover will try to convince the verifier that both polynomials had almost the same coefficients in that basis, but permuted. So this is a problem that I have came across many times in my very short career, which is a permutation argument, basically. I have two polynomials in the same basis. Two polynomials that in the same basis have the same coefficients but permuted. If you're familiar with Plonk, I have, for instance, for the first time came across this while trying to do something more efficient than Plonk. Spoiler alert, it won't be more efficient, but it's simpler. So basically, I want to prove that the coefficients of these polynomials are just perfect. So this is actually how I work while trying to design snarks. I don't think of groups at all. I think of polynomials. So one observation here that I keep doing every time I come across this polynomial is that these two vectors that are one permutation of the other, of the vectors of the coefficients, actually share some encoding. Because if I build a polynomial that vanishes at all of the elements of Pi, and then that vanishes at all the elements of sigma, the W, that is the permuted V, and these polynomials are minimal, then they must be the same, right? Because the coefficients are the same, and because I have a product, I don't care about the order. So this is my first observation. I want to prove that two things are permuted, and there is one encoding of these two vectors that would be the same for both. And now, what I also see is that when I evaluate this T, this encoding in V, or for the case W is the same, I get a polynomial with degree D to the 2, which is not efficient, but doesn't matter, with the following property. Whenever I evaluate T on V on HI, it will be 0. Why? Because every time I evaluate V in HI, in one of the elements I build the basis with, I will get one of the VIs here. I am interpolating the vector. So my interpolation points are the H's. Whenever I evaluate it in one of them, one of these products will be 0. Right? I will get yes or yes, one of the VIs. And then everything is 0. And that will happen for every one of the interpolation points.
If you get 0, you know that you've picked the right.
Sorry?
If you get 0, you know that you've got the right value. Is that?
Yeah, that's the idea. So again, basically I have a polynomial that interpolates a vector, and then I have the vanishing polynomial of that vector. When I compose them, I will have a polynomial that vanishes at every interpolation point. On what is the same, X minus HI divides T evaluated in V for all the HIs in H, right? Same concept as KCG. So I will have one QI that such that T in V equals X minus HI times Q, but also I will have actually one QI for the product of all these X minus HIs, which is the vanished polynomial of the interpolation set. So if I prove this relation, I will be proving that the relation between V and T. But if then I prove the same for W, and I prove the relation between W and T is the same for both V and W, then I prove the relation between V and W. Do you have questions? Because I thought this was simpler. Like in my mind, it sounded simpler.
What is W? That's permuted.
W is the permuted one. So basically, I have one thing that they share, which is T. T is the same for V or for V permuted. So I want to relate them both to T. And if I can prove that they are both related to T, then I can prove the relation between them.
This is any permutation, right? If you want to fix the sigma and you want to show that this is exactly the way you permute.
No, my permutation is secret. Not zero knowledge. I'm not hiding it, but it cannot be a fix. That's also why this doesn't work for plot.
Does it not just prove set inclusion?
Hmm?
Does it not just prove set inclusion? Does it also take care of the multiplicities in the roots? Right, it's just proving that there is a root, like that they share that like an element is a root, right?
Multiplicity. Unless you have it.
I mean, I'm not interested in the roots of T evaluated in B, because then I will have much more. I'm interested in the roots of T.
Okay.
But it's a very good question. Like actually at some point, yes, I was like, I'm interested in the roots of T, and T is a polynomial of degree T. I'm not interested in the root of T evaluated in B. So the roots of T are the interpolations of P. But now, we have a problem here because I cannot prove this with a pairing. Why? How can I put T evaluated in B in the group if I have T in the group and B in the group? I cannot compose those polynomials, right? So here is where KCG comes to the rescue, and we will design a proving system for this relation. Both prover and verifier have B and W that have degree less than D. The prover will compute T, and then it will find Q1 and Q2 that prove that T evaluated in B and T evaluated in W vanish for all the elements in H. And then it will send the verifier T, Q1, and Q2. The verifier will reply with an alpha, and then the prover will say, okay, this is B in alpha, W in alpha, Q1 in alpha, and Q2 in alpha. Why? Because the verifier needs to evaluate B in alpha in order to be able to put it inside T. So I cannot do something like this. Okay, now we have it. I cannot do T of B of X, but if I have that B of alpha equals some beta, I can do T of beta. Alpha needs to be uniform, and then this must be true. Whatever I prove on T of alpha or beta must be true for all elements of X, except with a probability.
So I can prove or not cheat by using like either larger or smaller degrees for T. So the prover, like the verifier, knows nothing about T of X in a way, right?
No, because we haven't used yet KCG. But once I use KCG, T will be bounded. So this will work. As inefficient as it is, as Marco said, I forgot to put the degree bound of T. But if I put the degree bound of T, this works. Now, this is how I think when I work, right? This is how I try to find solution for certain snacks. But then, you have to prove that is sound if you want. You have to use Schwarzschild and it should work. If you want to do it and show it to me, I will be glad. But then KCG comes here. The compilers come here. Find your best. Prover and verifier won't have B of X and W of X. They will have commitments to them. The prover won't send T, Q1, and TQ. It will send commitments to T, Q1, and TQ. Q2, sorry. So this becomes a succinct argument. Well, still almost. No, it's already succinct. Then when the verifier sends alpha, my prover won't send B alpha, W alpha, because what does it mean for the verifier that? It will have to send the openings of B alpha and W alpha with a proof. Hey, this is the opening with respect to the commitments that we both knew at the beginning. And then for the equation that is this embedded equation, it will basically open all this polynomial also in alpha to prove that it's zero. Why? Because if this is zero in alpha, or a random alpha, it must be zero, except with some probability, of the degree of the polynomial over the size of the field, it must be 0 as a polynomial. That's where Schwartz-Zippel comes to play. And then the verifier, what it will do is check a lot of KCG. So I'm sure I have lost some of you here, but the idea is that with KCG, we can just work on an information theoretical object, prove that something is satisfying polynomial land, and then just use magic. Even more, if the prover wants to actually hide these commitments, there is a compiler that tells us, okay, do this, and then this will be also hidden. Here, I'm not hiding anything, it's just succiness.